This video will discuss some special kinds of matrices and some properties of matrices in general. So as I said, a matrix is a n by m rectangular array of scalar values. So we have each of these values here, which are an element, which have rows and columns in our matrix, n rows and m rows and n columns. For this video, we're considering square matrices, which are matrices where the number of rows and columns are equal, so they are n by n matrices. First case would be the identity matrix, a matrix which has 1 where I equals j in terms of the element number and 0 otherwise. So along the what's called the diagonal of the matrix, we have 1s and we have 0 elsewhere. I might be indicating this notation in the future by this type of 1 down the diagonal, dot, 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 and so forth up to element n, and then having these kind of bold zeros on the other side mean that we have zeros everywhere else. All right, that's an identity matrix, and its elements can be indicated by the Kronecker delta. So it's 1 if I equals j, and it's 0 otherwise. All right, next up is the inverse matrix. So a to the minus 1 is the inverse of a. So that is the matrix such that a minus 1 times a is equal to an identity matrix. And thus a times a minus 1 also equals an identity matrix. For a 2 by 2 matrix, we can write this out analytically. The inverse of a 2 by 2 matrix is 1 over its determinant times, you flip the diagonal elements, they exchange, a22 is now a12 and vice versa, and flipping the signs for the off-diagonal elements. And also, if we have a given case where A and B are both matrices which are n by n, if we have the inverse of a product, that's going to be the inverse of each matrix but in reverse order. Because if you imagine, if we have A here times B, remember matrix multiplication goes from right to left. So if we have b minus 1 times a minus 1 times a times b, the a times a minus 1 cancels, give us identity. B times b minus 1 cancels, gives us an identity. So it makes sense that a times b to the minus 1 is b minus 1 times a minus 1. This works as well for successive products. For a times b times c, the inverse is c minus 1, b minus 1, a minus 1, etc. beyond that. Another important property is the trace of a matrix. So for n by n matrices, the trace is the sum of its diagonal elements. So sum from I equals 1 to n of aii. So it's a11 plus a22, etc., all the way to ann. It's called the trace. For an identity matrix, an n by n identity matrix, all your diagonal elements are 1, so the trace of an identity matrix is equal to n. And a very convenient property for us is that the trace of a matrix is equal to the sum of its eigenvalues. So these set of lambda here I've called the eigenvalues, although I've been using the notation omega for most of this series, so maybe I should have used omega here. But in any case, the eigenvalues, the sum of the eigenvalues is the trace of a matrix. We'll explain what eigenvalues are in a subsequent video. All right, then we have the transpose of a matrix. So the transpose of A is this symbol T here, just as it was for vectors. So the elements of the transpose are we exchange the rows and the columns. So the aij of the transpose is equal to aji. So we're just trading, we're reflecting over the diagonal here. So an1 becomes a1n, a21 becomes a12, and vice versa. If a matrix equals its own transpose, then it's said to be symmetric. And if a matrix equals its own adjoint, it's said to be Hermitian. So this kind of cross-like symbol here, or a dagger, or whatever you prefer to call it, that symbol is equal to the transpose complex conjugate. So for the adjoint of a matrix, its elements are the transpose taken to their complex conjugate. So if I take the adjoint of A, a21 is a12 star, a2n star, a22 star, etc. Okay, and then we have a special case if the adjoint of a matrix is its inverse, that matrix is said to be a unitary matrix. Unitary matrices are going to be very important in quantum mechanics, more advanced quantum mechanics than is typically taught for undergraduates, but electronic structure theory and advanced molecular quantum mechanics, unitary matrices are everywhere. And if the transpose of a matrix is equal to its inverse, that's called a symmetric matrix. So if my adjoint is my inverse, then my adjoint times myself equals identity, and thus myself times my adjoint also equals identity. As I said in the previous video, the determinant of a unitary matrix is equal to 1, and now we see why it has to be, because the determinant of the inverse of a matrix is 1 over the determinant of that matrix. The determinant of a matrix times the determinant of its inverse has to be 1, because the determinant of an identity matrix is 1. So if your adjoint and the determinant of an adjoint and the determinant of a transpose is equal to the determinant of the matrix itself. So the determinant of a unitary or a symmetric matrix has to be 1. And for also that means for a unitary matrix that all of your eigenvalues have to be equal to 1 as well. So for a 2x2 unitary matrix, the special case of being a 2x2, we can represent all possible 2x2 unitary matrices in the following way. We define some angle theta, and the elements of this matrix are cosine theta, and the off diagonal being sine theta and sine minus theta. Unitary transformations are going to be used for transformations of a given basis set, and they're also kind of matrices that are somewhat similar to rotation matrices. So these are some basic properties of matrices that are going to be handy for the rest of this playlist that we will utilize to derive some useful results.